So before we start example 2, I just want to refresh your memory on a few calculus-related things. So first of all, it's important to remember that the derivative of a function is the instantaneous rate of change, or the slope of the function, right? We can think of it as the slope of a function at any given point, or the slope of the tangent line at that point, right? And so if the first derivative is greater than 0, so positive, then the function is increasing on that interval. And if the first derivative is less than 0, so negative, the slope, the function is decreasing, or the slope is negative, right? So if you take a look at these diagrams down here, you can see some examples of increasing and decreasing functions. So you can see in this example here, if we looked at the slope of the tangent line to any point on this curve, the slope would be negative. Okay, so this is a decreasing function. This is an example of a decreasing function. Now we can also see this is also a decreasing function. Has a little different curvature though, but it's decreasing. If we took any point on this curve and drew a tangent line, its tangent line would have a negative slope. Okay, so the first derivative of this curve would be negative, right? And so we can also see here that if we drew a tangent line to any point on this curve, we'd have a positive slope. Same way here, positive slope. So this is an increasing function, and the first derivative is positive. All right. Now in 108, you should have also been introduced to the idea of the second derivative, which is essentially the derivative of the derivative. And you probably learned a little bit about concavity. All right. If the second derivative is greater than 0, that means the slope is increasing, and we consider it to be concave up. So the curve, I always think of concave up as like a U, right? It's concave up. So the slope is the slope of the function is increasing. Okay. Now you can see here in this example here we have an example of concave up and increasing. Okay, so you can see down here, if I took a tangent line at that point, it's fairly shallow, and then if we take another tangent line up here, you can see the slope is increasing. Okay, the slope is increasing, which means it's concave up. So this is also considered concave up. It's a little bit trickier though, because here the slope is negative, and then it's becoming less negative down here. So it's still increasing. The slope is increasing, but it's becoming less negative. So these two curves here are examples of curves that are concave up. All right, and concave down then is the other way, right? When the second derivative is negative, it's considered that the function is considered to be concave down. The original function is concave down. So concave down looks like that. It's the upside down U. All right, U for up. And then if it's not a U, it's concave down. So concave down looks like that. And if the second derivative is negative, that means the slope is decreasing, right? The first derivative is decreasing. So you can see here, if you look at a tangent line down here, okay, it's fairly steep, and then it becomes more shallow. So you can see that the slope is decreasing. On this curve, the slope is negative everywhere. So you can see it's becoming more negative, right? So we could still say that the slope is decreasing, but it's becoming more negative. All right, so that's just a little review. Now let's talk about how we can use that information to find critical points. Okay, we're searching for local extrema. All right, and we kind of already hinted in the first example of how we might find that if the slope is changing from, if the slope is negative and then changes to positive, okay, so the function is decreasing and then is changing to increasing, just by looking at these two curves next to each other, there's probably a point here where we pass through 0, right? The slope is negative and then it becomes positive, so we're passing through 0. And that's essentially what we're going to define as a critical point. Any place on the function where the slope is 0, the first derivative of that point, is 0. Okay, so for any function f at a point p in the domain of f, where f of p is equal to 0, so f prime of p is equal to 0, so that's the derivative of the function. We're looking for places where the derivative of the function is 0 or undefined. Okay, that's a little technicality there. For the most part, we're going to be working with continuous functions, though, so you won't have to worry about places where the function is undefined too much in this class. That's considered a critical point. Any place where the first derivative is 0, okay, which means the slope is 0, which means that it could be possibly changing the slope, or the function itself could be changing from decreasing to increasing or increasing to decreasing. Okay, so so any point where the first derivative is 0 is considered a critical point. Okay, that's the first step in finding a local maximum or minimum, is finding those critical points. So that's what we're going to do in example 2. We just want to find the critical points. We're not going to find extrema yet. We're just going to find the critical points of this function. And what are we going to do? We're just going to take the derivative of this function, right? So I'm just going to use the power rule and take the derivative of this nice little polynomial. So I get 3x squared minus 18x minus 48. All right, and I want to find where that is equal to 0. Well, it's a quadratic, right? So we have to factor it. First thing I'm going to do is factor out this 3, because that just makes it complicated. If I take out the 3, then it's a little easier to factor. Okay, so let's factor out the 3, and so then I get this. Okay, I'm looking for where that's equal to 0, but I want to factor it. So I'm going to factor this quadratic. So I'm looking for factors of 16, negative 16, that add to negative 6. Well, negative 8 times a positive 2 would multiply to negative 16 and add to negative 8. So I'm going to factor this into x minus 8 and x plus 2. All right, now I can solve this. And you can see that the critical points then are going to occur, when x is equal to negative 2 or 8. Right, those are the points that cause the first derivative to be 0. Now I want to go back to the definition. There's a few more little nuances here that I want to point out. So these are considered critical points, and if I evaluate the function at those points, so if I just take the original function and I plug in a negative 2, I get the value of the function at that point. Okay, so if I put in negative 2 and do negative 2 cubed minus 9 times negative 2 squared and so on, just put negative 2 into the function, I get 104. All right, this is considered a critical value. All right, so that's what I have here. It's the value of the function at the critical point. Okay, so again, I can find another critical value by evaluating the original function at 8, and I get negative 396. Okay, so those are considered critical values. Now, critical points are most oftentimes referred to as just the x-coordinate, but you can also refer to critical points. Critical points by the coordinates of the point, right? So you can also consider the critical points to be negative 2, 104. That would be the complete point, right? The x and the y value. So 8, negative 30 or 396 would be the other critical point if you wanted to refer to the actual point. But for the most part, we're going to be just referring to the critical points by their x values. So that takes care of that example, and I'll meet you in the next video.